41, I see it. F of theta equals 2 cosine theta plus sine squared theta. Good. So instead of this problem that I did not get the chance to look at, we're going to do this one. Is that okay? So there is one problem here that was left over from 4.1, which is this. Instead of this function, we're going to look at 41. And we don't have to go back to that one. Perfect. Good. So in this problem, we are asked to find the critical numbers of this function. What do I have to find? This function is defined everywhere. Sine is defined everywhere. Cosine is defined everywhere. So I'm asked to find the critical numbers. What do I have to write? Or what am I trying to do? What am I trying to calculate? In order to find critical numbers, I need to find? Very good. Thank you. So that is 2 sine theta plus, very good, excellent, good. So knowing that the first derivative is made out of sine and cosine, it can never be undefined. So the only critical critical numbers can come only from one source in this case, only from f prime of theta being 0. We agree? Okay. So I have to set all this equal to 0, and I will factor out 2 sine x. 2 sine x, -1 plus cosine theta equals 0. Do we agree with this step? I have two terms. Both of them have 2 sine theta in common. I pulled it out. I have -1 plus cosine. Correct? Okay. 2 cannot be 0, but there are two possibilities for this to be 0. Either sine theta is 0 or cosine theta is 1. Is this acceptable? Yes? Okay. Now I will have to solve each trigonometric equation separately. So I have sine theta equals 0. I go back to the unit circle. I remember that sine is measured on the y-axis. So where is sine 0? Here at 0, right? And pi and 2 pi. So 0 and pi and 2 pi, if you want to say that. Perfect. So there are two options. Theta equals 0 plus 2 pi k. K is plus or minus 1, plus or minus 2, and dot, dot, dot. And the other option is theta equals pi plus 2 pi k, and k is any rational, any integer. So why do we need to put this k? Now, if I don't put this 2 pi k, then I'm only referring to these two solutions. But there are infinitely many solutions. So 0 is here. If k is, oh, I forgot. I'm sorry. Also 0. 0. Okay. So let me write this one more time. K equals 0, comma, plus or minus 1, plus or minus 2, and so on and so forth. So if k is 0, then I get 0. But if k is 1, then I get 0 plus 2 pi. If k is 2, I get 0 plus 4 pi. The same thing with pi. So if k is 0, I get pi. But if k is 1, I get pi plus 2 pi. Or pi plus 4 pi, and so on and so forth. So this is a complete set of solutions. Of course, you don't have to write 0. 2 pi k is good enough. Now, of course, you can also combine these two in just saying pi k, which is fine. These two will be condensed into, I don't know how the solution is presented. It doesn't matter. Okay, so now I have to solve the second equation, which is cosine theta equals 1. So where is cosine 1? Cosine is measured on the x-axis. So where is cosine 1? Only here. but this is already included. I don't have to write anything for that because it's already included. I already have 0 plus 2 pi k. So the solutions are these, or if you want to condense them, I would say pi k. Again, I don't know. You don't have to condense. I'm happy if you just write those two. But if you write pi k and k is 0, then you're here. If k is 1, then you're here. When k is 2, you're here. So you could write pi k. And k has the same characteristics in order to condense these two. Or you just leave them alone and I'm fine. Very good pick. Thank you for that. Good. Anything else? Is there anything else you worked on? 45 page or section? 45. Okay. Let's take a look at 45. 45, 45, 45. A formula for the derivative of a function f is given. How many critical numbers does f have? So we have f prime equals 5 e to negative 0.1 times the absolute value of x times sine x and minus 1. So this is the derivative of a function. How many critical numbers does it have? So what will I have to do? First, I'm looking at this function. I don't see anything that will create an undefined situation, right? So let's look at the two options for the absolute value of x, and let's analyze when this is 0 and potentially undefined. We'll see in a minute, but I don't see any. This is always defined. Even if it's 1 over, it's not going to make it a difference. 1 over e to a number, if it's 0.1x or negative 0.1x, it's not going to make any difference. This is always defined. E to a number is defined on all real numbers. So there will not be critical numbers coming from f prime being undefined. But I still would like to see both options. So the absolute value of x, I know, is x for x greater than or equal to 0. It's negative x for less than 0. Would you agree with this? Therefore, I will have two options for the function, for the derivative. I'm sorry, we are given a derivative. So then f prime of x is two options: 5, and if it's x, e to negative 0.1x times sine x minus 1. And the other option, of course, for x greater than or equal to 0. And the other option would be 5e to 0.1x times sine x minus 1 for x less than 0. Very good. Perfect. So now I will set this equal to 0 and hope to get something to the right-hand side of 0 as solutions. And then I will set this equal to 0 and hope to get a solution that is negative. So 5e to negative 0.1x sine x minus 1 equals 0. This is 5 sine x over e to 0.1x minus 1 equals 0. Or 5 sine x minus e to 0.1x equals 0. After I found the least common denominator, and the fraction is 0 only when the numerator is 0. Now the question one more time is asking us to use the graphing calculator, as you see, because I can't solve this by hand. So you see the graphing calculator symbol for these problems 45 and 46. So I could think in terms of the intermediate value theorem because they are both continuous functions. So this is a continuous function. I could plug in numbers to see what's happening there. I don't know how high I would go. I would graph these two functions separately, 5 sine x and e to 0.1x, to see what happens, and study it a little bit because I have no other options but the graphing calculator. I could also find, we haven't gotten that far yet, I could also look at the second derivative and see whether there are any solutions. Because if the second derivative, it shows only positive or only negative, there may not be solutions at all. But I have to graph, because I don't know where they intersect. So in y equals, I will create two functions. One function will be 5 sine x. I want to make sure that the mode is in radians, okay. And I will create the other function as e to 0.1x. Second e parentheses 0.1x. And I'm going to graph them, I'm going to say for now standard viewing window. So I'm going to say 6. Of course, this is 5 sine x. It goes to as high as 5 and as low as -5. And e to 0.1x is the red graph. So it only is asking how many critical numbers does f have? So this is just the positive part of x. So for x greater than or equal to 0, how many critical numbers does f have? I'm solving the derivative equals to 0. Let me go further to the right as far as I can to x. Let's say I'm going to say 100, and let's see if it at some point in time it should exceed 5. E to the x should exceed 5 and move away from sine x, 5 sine x. So the red graph is coming up. Okay, so this equation clearly for x greater than or equal to 0 has 1, 2, 3, 4, 5, 6 solutions. So 6 different x values that are positive. And I can determine them, but this is not the point. We're not asked to find all of them. I will, if we want to find one, I would use the intersection. So second and calc, and the intersection is 5. And let's say I want to determine this one. So let me see if it's better to. Okay, I'm going to just put in a number. I'm going to put in 1 or 2. No, I didn't mean that. Second and calc, I want the intersection 5. Okay, first curve, no, that's not the first curve. The first curve. Oh yeah, that's the first curve, but I have to give it a boundaries. Okay, that's first curve, yes, it's true. That's the second curve, yes, it's true. And I'm going to guess, this was 0 to 100, so I'm going to guess 4. It's going to give me one of them. So it's giving me this intersection. So I can determine each and every one of them. So I have 1, 2, 3, 4, 5, 6. So 6 on the positive side of x. But now I have to go back and solve the other equation. So I'm going to say here 5 solutions that are positive. But then I also have to look at the other one with the left-hand side. And then I will have to solve this. So this is 5 e to 0.1x sine x equals 1. So it's a totally different story, different graphs, different functions. So I go back to y equals, I clear everything else because it's a totally different thing. Y2 is 1, and y1 is 5 e to parentheses 0.1x. Don't rush so hard. Software, wait, I didn't finish. So sine x. Okay. So I'm going to use the standard for now. I have no idea. Okay. So here's the 5 e to 0.1x times sine x. We are only going to look at the negative side, so I don't care for this side. Thank you very much. So here's coming y equals 1. So I have to go as far as I can to the left-hand side. Very interesting problem. I'm going to go -50. And x maximum, I don't care for that. Maximum 2. I don't know much about negative. I'm going to say negative 5 to 5. Because once it goes below 1, I'm done. Okay. So here is, now it's increasing. Yes. Okay. Interesting. Very interesting because of e to the x. And now here's come 1. Aha. Okay, right here, 1, 2, 3, 4, 5. Everything else I don't care for because I'm on the negative side. So I'm assuming that this is a touch here. I have to check. But if it is, I'll say 1, 2, 3, 4, 5 for the negative side. So 5 solutions that are less than 0. So for a total of 10. Any questions on this? Is this okay? Any questions? Was this assigned? Good. Okay. Did they say 10 at the end or less or more? Okay. Very good. Perfect. Anything else? Interesting. I'm going to thank the math department for choosing that. It was interesting. Good. Anything else for me? Good problem. Well done. Well done, math. Questions? Yes, Tony?
Could we quickly look at number 11 on page 280?
Yes. 11 on 280. Very good. 11 on 280. 11. F has no local max, or sketch the graph of a function f that is continuous on 1, 5 and has the given properties. So continuous on 1, 5. F has no local max or min, no local max or local min, but 2 and 4 are critical numbers. So critical numbers 2 and 4. So a continuous function 1, 2, 3, 4, 5. Continuous on 1, 5. No local max, no local min, which means it cannot have a turn.
I think this is number 10. Maybe.
I know it is. I'm sorry.
No, it's fine.
I'm sorry. Sketch the graph of a function that has a local max at 2 and is differentiable at 2. Sorry about that. Sorry. Okay, number 11. Then starting from scratch. Sketch the graph of a function that has a local max at 2, local max at x equals 2, and differentiable at x equals 2. So it has a local max and is differentiable at x equals 2. Has a local max and is differentiable at x equals 2. Sketch the graph of a function that has a local max at 2 and is continuous but not differentiable at 2. Very nice. So this was part A. Continuous, not differentiable, but it has a local max at 2. Very good. Continuous, not differentiable. Oh, I'm sorry. Continuous, not differentiable at 2, but local max at 2. Part C. Sketch a graph of a function that has a local max at 2 and is not continuous at 2. Local max at 2 and is not continuous at 2. Say it again. But it has a local max.
But if you do a jump on both sides, you're still coming down to the side of it. Would that mean that it's fulfill this condition?
So you want to graph it like this?
Yeah. Would that work?
But it's not continuous here, but it doesn't have a local because I cannot show the open interval.
Okay.
Sketch the graph of a function that has a local max at 2 and is not continuous at 2.
Could you do kind of a plus?
But this is continuous at 2. It says not continuous at 2.
I think the book actually has an answer like that, though. If you have it on C, it's a separate graph. Like it's like a half a parabola and then the other line straight off of it underneath. So it's a little weird because it technically isn't what you say it is, but that's what the answer in the book is.
I think the student who wrote the solution on this made a mistake because they normally
That's why
sketch
I
the
asked.
graph of a function. So is it here? Is it at the end? 11C, 11C, 11. What's chapter 4? Chapter 4, 11C. Chapter 4, 11C, 11C, 11C. There is no local. They may have meant absolute, but not local. It cannot be a local. Like I have to show you the open interval. Actually, the open interval exists. It is true. They are correct. I'm wrong. The open interval doesn't have to be. It's so if this is open and this is closed, because one of them has to be open. Actually, it is. So I can show the open interval. So the function between, this is 2. So I can show the open interval around 2, and all function values are less than this. I'm wrong. They are correct. Yes, I can. I can show, I can still show the open interval. Yes? Good. Thank you. Yes, that's correct. It's acceptable. Because I can still show the open interval. As long as I can, even if the left-hand side is somewhere else, the function values are smaller than the function values here. Perfect. Thank you. My mistake. I apologize for that. It is correct. They are right. Sorry, student who wrote. I apologize. Who wrote the solutions for this? Okay. Yes. Anything else? 15? 289. Very good. 15 on 289. Let x be, f of x be x minus 3 raised to negative 2, which is the same with this, in case I need one or the other. Show that there is no value of c in the interval 1, 4. We had an example together. Actually, I think we did just this one. Actually, it was a problem that we didn't get to, which is very good. It will replace this one. Because it's very similar. This one that I did not get the chance to show. Okay? You may have a different target or a different answer, but it's very similar. Okay. So let f of x be, so show that there is no value c in the interval, so c in the interval 1, 4, such that f of 4 minus f of 1 equals f prime of c times 4 minus 1. Why does this not contradict the mean value theorem? Excellent. So remember, the mean value theorem requires 2 conditions or 2 hypotheses. The function has to be continuous on the interval 1, 4, and differentiable on the interval 1, 4, but it's not. It is not. It is not continuous. on 1 comma 4. The function is undefined at 3. So it has nothing to do with the mean value theorem. It does not contradict it because the mean value theorem cannot even be applied here since the function is not continuous. That's why there is no contradiction. So C does not exist. The function is not continuous between 1 and 4, being undefined at 3. That's why I changed it, so we can take a look and see. Clearly, it's not defined at 3. You can't show anything. You can only say the mean value theorem is not applicable. C does not exist. The function is not continuous. Good. Anything else? Anything else?
Can you do number 7, page 288?
Yes, number 7 on 288. Let's take a look. 7, 7, 7. Use the graph of f to estimate the values of C that satisfy the conclusion of the mean value theorem for the interval 0, 8. Very good. So first of all, remember we have the mean value theorem requires that number 1, the function is continuous on the interval 0, 8, and number 2, differentiable on the interval 0, 8. Is this true for the given function in the graph? Perfect. Okay, so now we are asked to estimate these C values. So also remember that f prime of C, so this is a different way of writing the mean value theorem. So remember we wrote it as f prime of C as f of 4 minus f of 1 over 4 minus 1. So they multiplied both sides by 4 minus 1. It's the same thing. Okay? So f prime of C will have to equal f of 8 minus f of 0 divided by 8 minus 0. F of 8 in the problem. Can anyone identify f of 8? Oops, I have to count. 2, 3, 4, 5, 6, 7, 8. Can anyone give us f of 8?
Great.
Good. Can anyone give us f of 0? Good. So I have to find points at which the slope is 3 over 8. Rise of 3, run of 8. Also, let me dig up my pencil. I got it. So now, on the graph, I will have to draw this line like we did before when we talked about the mean value theorem. I missed it. Okay. So then I'm going to continue drawing a horizontal, a parallel line to this, right above here. Going to continue drawing a horizontal, a parallel line right above here, about here. So I will say this appears to be the point I'm interested in, and somewhere here it appears that this is the point I'm interested in. This is roughly 3. I'm asked to approximate. The problem says estimate. Okay, so I will say that this is about 3. 1, 2, 3, 4, 5, 6, 7. I don't know, maybe 6.4. So these are the points at which f prime of C, f prime of 3 is roughly 3/8, and f prime of 6.4 is roughly 3/8. Of course, my graph is not perfect. I'm asked to estimate, so roughly that's what I came up with. Yes, Ben?
Wouldn't it be one very close to 0?
I'm sorry?
The line crosses over the beginning of the function, so wouldn't it be a parallel line really close to, very close to 0?
This one here? Yeah, so you're saying that my graph is not perfect of this line?
No, what I'm saying is like because the
But-
the secant line crosses back over the function, would there be a tangent line really close to zero?
Somewhere here, yes, I see it. I see it. Yes, there is one more point here. Yep, I see it. Yep. Yeah. So another point somewhere here, which is very difficult for me on the graph to estimate. Yep, it appears that it crosses. I didn't even look. I didn't take my glasses off to take a look at this carefully. Yes, it is. You're right. Thank you. Yep. Good. Something like this. Is this better? Does it answer your question? Okay, very good. Anything else? Anything else? Very good questions. Very good questions. I'm erasing it because I may have to show it again. Who knows? Next time. Good. Okay, can we move on? Since we went through all these problems in almost 45 minutes, is that okay if we continue? We can come back to other things later if we want to. So let's continue with 4.3. How do derivatives affect the shape of the graph, of a graph of a function? This is a very important section. And this is basically the foundation of graphing of any function with absolutely no graphing calculator. I'm not saying that I'm going to take it away from you. I'm only saying that you will be able to do everything by hand with absolutely no graphing calculator. So, which we were not able to do before. Let's talk about increasing, decreasing. We already talked about this, but I would like to fill it in. So we say that a function is increasing on the interval x1 comma x2. Of course, if f of x1 is less than f of x2. It could be considered f less than or equal to x2. A function is decreasing. So this is section 4.3. Is decreasing on the interval x1. This is what we know from pre-calc. If f of x1 is greater than f of x2. So let me illustrate this with a graph for each situation. This function is increasing on the interval x1 comma x2. Why? Because this is f of x1 and this is f of x2. So the function is increasing between x1 and x2. It could be decreasing for the interval or on the interval x1 comma x2. Why? Because f of x1 is smaller than f of x2. So it's decreasing. So this is for increasing function, f of x1 less than f of x2. And this is for decreasing function, f of x1 is greater than f of x2. But this is what we know from algebra, from pre-calculus, and so on and so forth. Now let's look at the first situation. We discussed this last time. Look at the slope. The slope of this graph is given by f prime, like here. The slope of this graph is given by f prime. So what can you say about f prime when the function is increasing on the interval x1 comma x2 if we want, or as I graphed it everywhere? What can you say about f prime for this situation?
Positive.
Exactly, it's positive. That clearly states, as we did last time, remember, when we compared the sign with the values. And what happens here when the function is decreasing? The first derivative will be Exactly. As you see, the slope is negative. Slope of the tangents. Good. So that's what I meant here. If f prime is greater than 0, then the function is increasing. If f prime is less than 0, obviously, then the function is decreasing. We already talked about the first derivative test, but I didn't tell you that that was the first derivative test. Now I'm telling you. So let C be a critical number of f of x. In other words, C comes from solving f prime of x equals 0 or f prime being undefined. So I know it's a critical number somehow. If f prime changes its sign at C from positive to negative, look at me for a second, from positive to negative, then f has a at C.
The maximum.
Local. Absolutely. It has a local max. It could be absolute as well. I don't know. I have to look at the function. If f prime changes its sign at C from negative to positive, so let's look now from negative, 0, positive. What does this function have at C?
Local max.
Exactly. If f prime does not change its sign at C, then C is
Constant.
not a local, does not give, or it's not, C is not a nothing. It's nothing. It's not a local max. It does not give a local max and does not give a local min. It is nothing. Find the intervals of increasing or decreasing behavior for these functions. But before that, I would also like to talk about concavity test. What does concavity mean? If a function opens up, we say it's concave upward. If it opens down, we say it's concave downward. Okay. What happens if a function opens upward and then at this point turns, not turns in the sense of max or min, it changes concavity and then it opens downward. So it kind of looks like this, like x cubed, right? X cubed is opening up here, but opening down here. What is this point? Not a max, not a min. When the function changes concavity, that point is called inflection point. Inflection point. So an inflection point is a point at which a function changes concavity. So I'm coming back here to concavity test. How will I know when the function opens upward or downward? I have to find the second derivative. So the second derivative, if the second derivative is positive, then the function opens upward. If the second derivative is negative, then the function opens downward. So if the second derivative is positive, then f is concave upward. And if the second derivative is less than 0, negative, then f is concave downward. Where the second derivative changes sign, that will be and it's 0 and changes sign, that will be an inflection point. If x0, a value of x, is a point of inflection, that the second derivative changes its sign at x0. Furthermore, if the second derivative is continuous at that point, then f prime of x is 0 of that point. And the second derivative test. I personally use the second derivative test very rarely. I will explain it to you, and you're more than free to use it. So I'm going to come back to this in a few minutes after we address that, and we talk about inflection points as well. And then we'll have these examples. And we can choose other examples if you want to choose. We can choose anything else from the book. But for now, this is what we discussed last time, and here it is, if you'd like to go back for a second. Here it was with a chart. Okay, here it is. So that was the first derivative. We determined the critical numbers, and we studied the sign of the first derivative. And this is the first derivative test. We did that last time. I didn't tell you it was the first derivative test, but I'm telling you now. So if the derivative changes sign from positive to negative, we identify this point, negative 1, 1, as the local max. Here, the first derivative did not change sign. It was negative, negative, mixed left and right of the critical number. So this was not a point of interest, at least for now. I didn't study the second derivative. I don't know, it could be an inflection point, but we didn't get that far. Now here, this point 1 comma negative 3, since the first derivative changes sign from negative to positive, then that must be a local minimum. This was the first derivative test that we already used last time. So now let's choose and do the same thing one more time for any of these functions. I wouldn't do all of them because I like to move on, and we can come back more examples, or if you want to choose 2 of those, we can choose 2 of those. So we are only asked to find the intervals of increasing or decreasing. We already did that, but I need to work on another problem. Please choose. Which one? A, B, C, D. C. I think we did C, but we did C. Yeah, we can do both. I'm just looking to see if we already did that. It was 9 minus x squared instead of 4 minus x squared. So we will have to find the domain, and then it's the same function. I just replaced 9 by 4. So let's do D. D was the one that you wanted? Okay, very good. Let's do D. So we have f of x equals x to 2/3. We're asked to find where this function is increasing or decreasing without graphing it, of course. So we apply what we know now about the first derivative test. So of course I have to find the domain is, so this function is the cube root of x squared. So this function is defined everywhere. No questions. It's a cube root, friendly function. It's not a square root. Again, I highly recommend putting the first derivative first and then the function in the middle, and then we'll follow with the second derivative. And I would like to edit now. From now on, the entire semester, you're going to see all 3 functions together. I have to write the domain, which I know it's the cube root. Domain is all real numbers, no questions there. I will find the first derivative as 2/3 times x to 2/3 minus 1, which is negative 1/3. And then I have 2/3 times the cube root of x. So the domain was all real numbers. Now I found the first derivative, and I have to find what? What is my next step? Mandatory now. After I found the first derivative. That was the reason why I found the first derivative, in order to identify critical numbers. Is this fraction ever 0? Because as you know, critical numbers come from 2 sources, from f prime being 0. Is this 0? Ever? No, because a fraction is 0 only if the top is 0, but 2 is not 0. And I can make it into 0. So there are no critical numbers coming from f prime being 0. Now, is this function undefined? At? Right. So at 0, the first derivative is undefined, and the second derivative will be undefined. Not the function, though. The function is defined everywhere. So please plug in 0 and tell me what you get, because I need to find the value of the function at 0. How much? Perfect. Good. So I know there is a critical number. I'm going to write it on the side. X equals 0, critical number. Coming from f prime being undefined when the function is defined. Perfect. Now, I need to study the sign of this function. I have to fill it in here. So, when x is a positive number, what kind of number will I get with a cube root on it? When I plug in x, a negative number, what will I get for this? Absolutely. Now, I need to find this. And I need to find this, which means you thought that the limits were gone. No. I need to find the limit of f of x when x approaches negative infinity. And I need to find the limit of f of x as x approaches infinity. Look at this function and plug in infinity and then plug in negative infinity or in any order you want. So, and tell me what are the limits here. That's why it's very useful to write it in this format, because here it's maybe more difficult to see. So when x approaches infinity, what does this approach? Perfect. When x approaches negative infinity, what does this approach? Perfect. That's all I needed. Now I have to make sense of these two. This is the moment in which I catch my mistakes. If the first row, I disregard this one, it's another row, right? If the row of the first derivative and the row of the function do not work well, I have a mistake. Okay, so let's see. From infinity to 0, what does this function do? Right. Is this fact supported by the sign of the first derivative? Therefore, I know the function is decreasing. What does the function do from 0 to infinity? Is this supported by the sign of the first derivative as we know it from the first derivative test? Yes. So then, in order to answer the question, when is this function increasing and when is this function decreasing, once I have the chart, you don't have to write it aside. I'm done. That's all I need to see. Now, if you want to write it by hand, write it by hand. But this is very good enough for me. You showed that from infinity to 0 it's decreasing, and that's supported by the sign of the first derivative. You showed that from 0 to infinity is increasing. Of course, from 0 to infinity it's increasing, and this is supported by the first derivative, and I'm done. Also, I would like to determine the second derivative now and discuss the second derivative as well. So I'm coming back to this. I'm not going to differentiate that. I'm going to differentiate this to find the second derivative. So the second derivative, I have a 2/3 in front. I'm multiplying it by negative 1/3 times x to negative 1/3 minus 1, which is negative 4/3. So this is negative 2 over 9, the cube root of x to the 4th. Okay. So now I would like you to tell me, is this ever 0? No. Okay, very good. It's undefined where the first derivative is undefined, so there is no problem there. But I would like you to tell me the sign. Plug in a positive x, plug in a negative x. I don't care what you plug in, and just tell me the sign of this expression. I only need the sign. Always negative. What does that mean? That the function is always opening downward. Always opening downward. So here's how I express that. That's the symbol that I like to use in my charts. So I know that this function opens downward at all times. Any questions? Any questions? So what will I say about this function? It's decreasing on negative infinity to 0. If you want to put this in writing, I don't need it. Once you show me this, I'm fine. It's increasing between 0 and infinity. It has these limits. And it's always opening down. Any questions? Okay. Next problem. Where are we? Here. Would you like to choose another to discuss this? Or we move on to these problems. And I will also explain the second derivative test when we get to any of these problems. I'll come back and explain the second derivative test. Say it again. Yes, please. Let's choose. Now, if we choose from here, then we'll show all of them. Anyway. Okay, so let's choose from here. Anything you want. Or we can all work on all three.
We work on all three.
Okay, so let's start with f of x. 5 minus 3x squared plus x cubed. So instead of reading all this, I'm going to say everything. Everything. The graph, the first derivative, the second derivative, everything. Okay? Okay. As you see, since the second derivative does not change sign, there is no point of inflection. When the second derivative changes sign, then there may be a point of inflection there. But it never changes sign. It's always concave downward. So it cannot have an inflection point. Good. So let's get the chart going. I'm hoping you will be using a chart of your choice. I do not take credit for this chart. I had a professor who taught it this way. So I wish I could take credit for it, but I can't. The domain of this function first, please. Once you fill up the chart, then you know you're done. Right, it's a polynomial function. Very good. Perfect. Okay. Now, I need to determine things about the function first before I even attempt the first derivative or the second derivative. So for the function, I have the domain. I should determine the x and y intercepts. And I should also determine the limits at infinity. Limit of f of x as x approaches negative infinity, and limit of f of x as x approaches infinity. This will give me everything I need to know about the function from the function itself. And then I move on to the first derivative. I have the domain already. You already told me it's a polynomial function. Now the x and y intercepts. The y-intercept is the easiest because I plug in 0. When I plug in 0, I get 5. Now the x-intercept, I'm stuck. Why am I stuck with the x-intercept? Because it's a cubic function. I don't know how to solve this. I have to use a calculator. And I have my magic calculator, in which I put a polynomial of order 3. I put in the coefficients in order 1, -3, 0, and 5. And I just hit solve. It's a 86. You don't have it. So the solutions are, so the first one is imaginary, of course the second one is imaginary, and only the third one is real. So the only solution is negative 1.1. So negative 1.1, and the answer is 0.
So if we don't have one of those calculators.
You have to do the zeros. So with the other calculator, did I exceed 50 minutes? Oh no.